most important downstream process is chromatography. Chromatography can be used for separating biomolecules, proteins, carbohydrates, peptides, and even small molecules, metabolites, small organic molecules. And because of chromatography it was possible to purify proteins to a very high degree of purity. There are different types of chromatographies, each one working on a certain principle, and that is what we are going to look at in the next few classes. So chromatography is widely used in biochemical engineering, bioprocess engineering, biopharmaceuticals and medicine, and it is also used for separating out carbohydrates, fats, vitamins, small molecules and so on actually. So it has got a very wide range of application. So it can be used for separation, it can be used for purification, and also it can be used for identifying compounds. There is analytical chromatography which is called high performance liquid chromatography or high pressure liquid chromatography, that is HPLC, which is used for identifying compounds in a mixture. So basically what does chromatography do? There is a selective distribution of components of mixture between two phases. So you can have a stationary phase, you can have a mobile phase. So the solute gets distributed based on different principles, physical principles, and hence there is a separation of the various solutes. So various solutes may have different separating or partitioning effects which may lead to a separation of components from a mixture. So in a chromatography what are the various components present? We have a stationary phase, that is a solid or an immobilized phase. You may have an immobilized liquid, or you may have ions, or you may have ligands, or you may have hydrophobic molecules, all immobilized on a stationary phase. And then you have a mobile phase, that means it could be a solvent or a mixture of solvents, it could be a water and a miscible solvent or totally immiscible hydrocarbon, and this is called a mobile phase, and your solution is also sent in through the mobile phase, which gets partitioned between the mobile phase and the stationary phase. Sometimes you can also have a gas as your carrier, then it is called a gas chromatography, and you can have a liquid as a carrier, then it becomes a liquid chromatography. So typically the chromatography consists of a long column could be extremely long, it could be even 100 feet for example, which is packed, and then you are injecting the solute. So the solute is getting injected at the inlet. So the solute keeps travelling because of the interaction of the solute with the stationary phase components. So there is some sort of a adsorption, desorption or partition takes place. So the concentration of the solute that is moving is going to spread. So it may be a very sharp injection at the beginning, it is slowly spreading, and as it leaves the column it is going to spread out like a Gaussian peak. So generally we assume this to be Gaussian in shape, or we can call it normal distribution or bell shaped, but it is never so. We are going to see as we go along. There may be tails or there may be a very long start, okay. But generally if you look at a concentration profile, as it travels because of the interaction between the stationary phase and the liquid phase, the solute forms a spread, uniform distribution spread, and this is very common in all chromatography, okay. So if you have a mixtures of protein for example, which is injected at the inlet, and there is a solvent which carries this protein, and there is a packed column on which you have certain stationary phase material, the proteins are going to get separated because of the varying interactions they have with the stationary phase. There could be ionic interaction between the solute in the mobile phase and the stationary phase, and this ionic interaction could be varying depending upon the type of proteins present. So proteins which are having a very strong ionic interaction will travel slowly or they will get slowed down. Proteins which have weak ionic interaction will travel faster. There could be hydrophobic interaction. So proteins which have high hydrophobic interaction with the stationary phase will travel slowly. Proteins which will have less hydrophobic interaction with the stationary phase will travel faster. Or it could be a polar interaction. So proteins which have very high polarity will interact much more with the stationary phase, so they will travel slowly, whereas proteins which has less polar groups on its surface will not interact much with the stationary phase, so they will travel faster. So slowly as this protein mixture travels through the column, they get separated, and the protein which has the least interaction with the stationary phase will come out first. So the principle of interaction could be hydrophobic or polar or ionic or affinity or anything like that actually. So the proteins which have least interaction with the stationary phase will come out first. Proteins which have most interaction with the stationary phase will get retarded and they will come last. That is how you get the separation. This is how chromatography is able to separate proteins or small molecules or metabolites or any biomolecule into various components. Of course you are not going to get very sharp differentiation in the protein. Sometimes there could be a overlap which may be very close or they may be considerably different. So we are going to look at all these variations as we go along during the course of this particular topic. There are different classifications of chromatography. It can be a in a very broad sense a planar chromatography or a column chromatography. As the name implies, in a column chromatography we are going to use a column. In a planar chromatography we are going to have a planar surface like paper chromatography or thin layer chromatography. If you look at chromatography many years back, organic chemists used to use something called the thin layer chromatography to separate out components in a reaction mixture and possibly even identify whether the product has formed. If they have a authentic sample of the product, they will simultaneously run the thin layer chromatography and see whether the product has formed. So organic chemists have been using this chromatography for a very long time. If you look at the column chromatography, which uses a column and there is a mobile phase, there is a stationary phase. Okay. In the mobile phase it can be a gas, mobile phase you can have a liquid. Okay. So you can have a, in the gas you can have a gas solid chromatography or a gas liquid chromatography, and similarly in the mobile phase you can have liquids, so you can have a liquid solid, liquid liquid and so on. So different types of chromatographies are possible. So if you look at the stationary phase, it could be a bonded phase, you could have a gas solid, you can have a liquid liquid, you can have a gas liquid or liquid solid and so on. So all these various combinations are possible. So that particular table was trying to differentiate between the structure of the chromatography, whether it is a paper or a planar or whether it is a column or a tube. It was not talking about the physical principle. Okay. The different types of chromatography based on physical principle is what is shown in this particular slide. So if the separation is based on volatility, that means the boiling point and so on, then we use something called a gas liquid chromatography. If it is based on partition coefficient, then we have a liquid liquid chromatography. That means the solute gets partitioned between two liquids, okay, the liquid which is in the stationary phase and the liquid which is in the continuous phase. Similarly you can have a liquid solid chromatography, that means you have a solid stationary phase and a liquid, and your solute is getting partitioned between these two. If the separation is based on charge, that means positive charge or negative charge, then it is based on ion exchange chromatography. If the separation is based on hydrophobicity, that means because of hydrophobic nature of certain proteins, they get retarded inside the column, then we call something called a hydrophobic interaction or reverse phase chromatography. So hydrophobic forces are the key in deciding on the separation. If the diffusion of the proteins through pores is the key, then it is called a gel permeation chromatography or size exclusion chromatography, GPC. If the molecular recognition or a binding between a ligand and protein is what is important, then it is called the affinity chromatography. So you have large number of chromatographies possible, and each chromatography works on a certain physical principle. So if you have charged molecules, then I will go for an ion exchange chromatography. For example, I have salts, I have proteins, I want to get rid of my salts. Where do you get the salts from? Like you use salts for salting out ammonium sulfate or sodium chloride, then I want to remove that salt first. What do? I may go into ion exchange chromatography. If I have proteins of different sizes or different molecular weights, then what do? I can use a gel permeation or size exclusion chromatography. Suppose I want to remove a particular protein out of a mixtures of several protein, then if I know a ligand which is very selective for the protein, I may have the ligand immobilized on the stationary phase. Then what happens? The protein is bound only to that ligand, rest of the proteins do not bind to the ligand, because as you know, ligand protein binding is very selective. So only that particular protein is captured by the ligand, whereas other proteins are not captured by the ligand. So that is called affinity chromatography. So depending upon the principle which you want to follow, depending upon the mixture of proteins you want to separate, we may use different types of chromatographies, and all these chromatographies are already being practiced commercially for purifying biomolecules, biopharmaceutical products, protein and so on actually. A typical block diagram of a chromatography setup, this is how it is going to look at. So you have a solvent holder or a solvent tank, then there is a pump, then you are injecting your sample. So the solvent is the continuous phase, okay. Then you have the column containing the packed or the stationary phase, then you have a detector. There are so many types of detectors that are available, ranging from UV to refractive index to light scattering and so on actually. And then finally you will have the collector of the various fractions, and you can also have a data logging and data analysis programs and computer and so on actually. So the solvent or the solvent mixture flows through the pump and it flows through the column. So we can have two pumps and we can have two different solvents also, so that way we can change the polarity of the solvent or the continuous phase. We may move from highly non-polar to polar, or we can move from highly polar to non-polar type by switching from one pump to another. So a single pump is called an isocratic system, a double pump could be a binary system. So we can change the polarity by having two pumps and two solvent holders. We can collect each of the fraction that is coming out, and then you can do further processing of that fraction. We can further purify it, or we can do analytical to find out what is the nature of the protein, or we can take it for further downstream as well actually. So the important parameter that comes into picture is the partition coefficient, that is the concentration of solute in each phase, ratio of the concentration of the solute in each phase, K. So K is equal to Cs by Cm. Cs is the solute in the stationary phase and M is the solute in the mobile phase. So ideally you want very high partitioning, and you also want the partition coefficient to be constant over a wide range of concentrations, right. And if Cs is directly proportional to Cm, of course we call it the linear chromatography, and if K is equal to 1, that means the solute is equally distributed between the mobile and the stationary phase. So the value of K determines the speed at which the protein travels from the inlet to the outlet. So if the K is very large, so the protein is slowed down or retarded by the stationary phase, so it travels very slowly. If the protein wants to travel faster, then the partition coefficient has to be smaller. So if two components in mixture have Ka equal to Kb, that means I have two components in a mixture and each component will have a partition coefficient which could be called Ka and Kb, and if Ka is equal to Kb, then we are in trouble, because there is not going to be any separation happening, because Ka by Kb is equal to 1. So Ka should not be equal to Kb and the difference should be considerably large, so that we can get a good separation. Either Ka can be larger than Kb or Kb can be larger than Ka. Okay, if Kb is larger than Ka, then what happens? That means B is slowed down or retarded by the stationary phase, because more of B is going to get partitioned to the stationary phase. So B will be travelling slowly and Ka relatively will be travelling faster. So if Kb is greater than Ka, A will be eluting out first, whereas if Kb is less than Ka, then B will be eluting out first. And of course in a real protein mixture situation, we are not going to have only 2 proteins, we may be having even tens of proteins or even hundreds of proteins, okay. So this just shows a pictorially what is happening inside a chromatography. So you have a continuous phase solvent flowing in, we have a stationary phase. Suppose we have a liquid, then this is called a liquid partition chromatography. We have a stationary liquid, so the solute gets partitioned in the stationary liquid as well as the mobile liquid, okay, or solute or analyte, and this ratio, as I described in the previous slide, is called the K. So this is a typical liquid partition chromatography. So when the protein comes out of the column after a certain period of time, I said you may have something like a Gaussian or a normal distribution, okay. So typically at a time T0, we will call this as the retention time of the protein, the protein concentration reaches a maximum and then it goes down. So this particular graph can be called a normal distribution or a Gaussian distribution. So you are injecting at T equal to 0 and the protein is coming out at T equal to T0, and it will be coming out in a normally distributed shape. This could be applying for volume also, just like time we could call this as volume. After you have collected the volume of V0, the protein will be reaching a maximum concentration. So the retention time of the protein depends on flow rate of the mobile phase, obvious, right. So the flow rate is faster, retention times will be less. So flow rate is equal to V, that is the volume of the column, P, porosity of the stationary phase, divided by time, okay. So the retention time is a function of the volume of the column, the porosity, as well as the time required by a molecule of the mobile phase to pass through the column, okay. Now there is something called the corrected retention time, which is given by Tr dash equal to Tr, that is the retention time we calculate minus the Tm, that is the time required by a molecule of the mobile phase to pass through the column. That means if there is no interaction between the mobile phase solute and the stationary phase, then it is the time required for the molecule to just go through the column, and as I said the columns are generally very long, maybe even going up to hundreds of feet. So that time needs to be subtracted to get the corrected retention time Tr dash. So if you look at a chromatogram of 2 components, so this we call it as the baseline, this we call it as the detector signal, this could be your time, okay, this could be your time. So there is a peak coming out first, and this is the Tm, that is the time required for a molecule to travel from the inlet to outlet if there is no interaction of the molecule with the stationary phase material, and then you have component A coming out, component B coming out, okay. Now this is the retention time for component A, and this is the retention time for component 2 B, okay. But if you want to do the corrected retention time, we need to subtract this Tm from Tr1 and we need to subtract the Tm from Tr2. We can have different types of chromatograms possible, okay. Imagine I have a mixture of 3 proteins, I am passing it through a column and I am getting an output signal like this, protein 1, protein 2, protein 3, okay. So if you look at this compound 3 or protein 3, it is well separated from 1 and 2. So we can collect this and we can assume when we collect it will be 100%. But let us look here, we have both the compound 1 and compound 2 or protein 1 and protein 2 partially mixed together. So when I collect samples in this region I may get compound 2 also present, or when I collect here I may get compound 1 here also. So ideally I need to get a better separation of these 2 proteins if I want to collect 100%, whereas I can collect very pure compound 3 without any problem, there is not going to be any contamination with compound 1 and compound 2. So here I would say this baseline separation is not good, this is the baseline. So the baseline separation of compound 1 and compound 2 are not good. So when I collect in this periods of time I will be also collecting the other protein. So the retention time of solute is affected by many parameters, nature of stationary phase, that means what is the type of stationary phase I am using, the porosity, particle size distribution, so on, actually whether it is a charged, uncharged, whether it has got hydrophobic groups and so on. Composition of the mobile phase is a solvent, so what is the composition of my solvent phase, does it have water, does it have pure solvent, does it have mixtures of solvent, what is the polarity of the solvent mixture, dipole moment of the solvent mixture, viscosity of the solvent mixture and so on. Column dimensions, what is the length of the column, what is the diameter of the column, and finally the flow rate of the mobile phase, how fast the mobile phase is flowing or how slow the mobile phase is flowing. So all these parameters affect the movement of my solute through the column. So for a given stationary and mobile phase composition, the retention time of solute increases with increasing length of the column. So if I have a very long column, it will take much longer time for the compound to come out. If I have a very short column, it will come out faster, okay. Or the retention time of the solute increases if I decrease the flow rate of the mobile phase. That means if I reduce the flow rate of mobile phase, the compound will take much longer time to come out, obvious, isn't it? Now again let us go back to this retention volume, which is also same as retention time. So retention volume is the volume of mobile phase required to transport the solute from the point of its injection into the column and its passage through the column to the detector, right. So Vr is equal to Tr into F, F is your flow rate, T is your time. Now the corrected retention volume, again just like we did corrected retention time, we need to also subtract Vm. This Vm relates to the dead space volume, okay, or the void volume. Now, so Vr is equal to Vm plus K into Vs. There is another factor which is called the capacity factor or the retention ratio. So, it is a measure of the retention of a solute component. Okay. So, it is a measure of the retention of the solute component. It is a measure of time spent by a solute in the stationary phase relative to the time spent in the mobile phase, or it is also called mass distribution ratio, or it is also called solute partition ratio. So, capacity factor is given by this particular formula. S relates to the stationary phase and M relates to the mobile phase. So, it is the total amount of solute present in the stationary phase divided by the total amount of solute present in the mobile phase. So, how do you calculate total? Total is nothing but concentration into volume, that is why you have Cm into Vm. This is the total amount present in the mobile phase, this is the total amount present in the stationary phase. Okay. So, this is a measure of the time spent by the solute in the stationary phase, that is the S, vis-a-vis the time spent in the mobile phase, that is the M. If it spends more time on the stationary phase, then the capacity factor goes up because it comes in the numerator. If it spends less time on the stationary phase, then the capacity factor goes down. That means it spends more time in the mobile phase relatively. There is another term which is called the column efficiency. So, the efficiency of the process is related to the width of the chromatographic peak. Okay. If the width is very large, then what it means is you are having a sort of a spread of the product, whereas if the efficiency or the width of the peak is very narrow, that means the spread is much less. The length of the column occupied by one theoretical plate is defined as the height equivalent to a theoretical plate. Okay. So, there is a term called a theoretical plate. This is called the height equivalent of a theoretical plate, okay, and it is given by this formula H is equal to sigma square by L, where L is the length of the column and sigma square is the variance. So, generally good H value for a 90 micron bead is between 0.018 to 0.027 centimeter. Good H value for a 34 micron matrix is between 0.007 and 0.01. Ideally we would like to have the height to be very small. That means if your sigma square is very small, height of a theoretical plate also will be very small. So, all these factors determine the efficiency of the column. Okay. So, imagine once again a Gaussian type of peak coming out. This is called the base and this is called the half width. That means the width at half the maximum. So, if this is the maximum height h, this is half h, and this is called the inflection point or the steepest portion of the curve. So, we can draw a tangent, we can draw another tangent, this will look like a triangle and this is the steepest point. Now, this width W is equal to 4 sigma and this width W half is equal to 2.35 sigma. So, generally we assume the solute flowing through the column spreads into a Gaussian shape actually, but it is not always same. So, if you assume a Gaussian shape for the solute distribution, then we can write an equation for concentration. C is equal to C naught, that is the maximum concentration, e power minus T by T naught minus 1 whole square by 2 sigma square. Okay. T naught is the time at which the concentration exits, okay, that is the maximum concentration reaches at time T naught, and T naught sigma is the standard deviation of the peak. okay. So we can take a logarithm on both sides and then we end up with T by T naught minus 1 square is equal to 2 by 2 into sigma square logarithm of C by C naught, okay. This is just a mathematical manipulation so we can get an equation of this form. So this equation relates C naught, that is the maximum concentration, T naught is the time at which this maximum concentration happens, C is the concentration at any time t, T naught sigma is the standard deviation of that particular Gaussian curve. Just like t, we can also substitute V as well. So C is equal to C naught exponent minus V by V naught minus 1 whole square by 2 sigma square. V naught is the volume required to elute the maximum concentration which corresponds to that T naught here. So you see V corresponds to T here, V naught corresponds to T naught here, and here V naught sigma is the standard deviation, okay. So please note that V equal to Q into T, okay. Q is your flow rate, V is your volume, so flow rate into time gives you V. That is why we have similar looking equation here, except that you replace T with V and T naught with V naught. So the main assumption in this is the peak that is leaving a chromatograph is a normally distributed or a Gaussian curve, and once you assume it to be Gaussian, you know the equation for a Gaussian distribution, and hence you can say C as a function of time will look like this. C is as a function of time will be C equal to C naught exponent minus T by T naught minus 1 whole square by 2 sigma square, or C is equal to C naught exponent minus V by V naught minus 1 whole square by 2 sigma square. So this equation is very useful, and the main assumption here is the peak that is leaving the chromatographic column is normally distributed, uniform, and it follows a Gaussian type of relationship. Now let us go back again to the chromatogram. So you are injecting your sample here, and at time equal to T naught it is showing a maximum peak and it is falling down, okay. This is a Gaussian distribution. Now we call this as beginning of this rise as T dash and the ending as T, then amount of this particular component, suppose we call it I, component I eluted in this time, could be integral of C into Q into dt. Q is your flow rate, okay, C is your concentration varying between T dash to T. So this is nothing but area under this curve, okay. Total of ith solute in the column total, so we have to integrate throughout, that is why we integrate between 0 to infinity CQ dt. So this is the total of I in the solute, that is starting from 0 right going right up to infinity, whereas amount of I eluted between these two times we are just integrating between these two limits T dash and T, okay. So what do we do? Yield of I, the component will be integral CQ dt between T dash to T and divided by CQ dt between 0 to infinity, obvious, right, this is yield. The amount eluted we can integrate T dash to T Q C naught exponent minus T by T naught minus 1 whole square divided by 2 sigma square dt. So what do? We substitute for C here like this, okay, and then when you integrate you end up as yield is equal to half of 1 by 2 error function T by T naught minus 1 divided by square root of 2 sigma minus error function T dash by T naught minus 1 divided by square root of 2 into sigma. So the yield, if you are collecting the sample between time T dash and T, is given by this. What is this error function? Error function is nothing but square root of 2 by pi integral 0 to x E minus u square by du. So we can get values of this in tables for different values of x. So for different values of x we can get this integral, we can substitute here and here as well. So the yield of the ith component, if you are looking at it between time t dash and t, and if the peak is coming out at t naught, is given by this relation. A corresponding relation for volume will be, instead of t we substitute it as v. So half error function v by v naught minus 1 divided by square root of 2 sigma minus error function v dash by v naught minus 1 divided by square root of 2 sigma. So this is a very important equation because we want to know how much of the protein we are able to collect if I start collecting between time t dash to time t. A protein may be present in different locations inside the column, but you are just collecting between time t dash and t, assuming that t naught is the time at which the protein maximum concentration is observed and t naught lies between t dash and t. Ideally when I am doing a protein purification I want to maximize my yield, I want to collect as much of the protein as possible. But then there is a balance you need to strike. If I try to increase my the window of time, the impurities also may get collected, so the purity of the protein which I am collecting may be going down. Whereas if I decrease the window of collection, the purity of my protein of interest may go up, but the yield will start going down. So I need to strike a balance between both. So if t and t dash are equal, then there is no yield, obvious, and if t dash is equal to 0, but that means from time equal to 0 itself I have started collecting, the error function term containing t dash, that is this term, if t dash is equal to 0, the error function containing this term will be minus 1. So what will happen? Yield will become half of 1 plus error function t by t naught minus 1 divided by square root of 2 sigma. So if I am collecting from time equal to 0 to some time t, then the yield will be half of 1 plus error function t by t naught minus 1 divided by square root of 2 by sigma. Now there is something called purity. A protein mixture may contain several proteins, n proteins. So when I am collecting the ith protein, I may be also collecting some amount of the remaining proteins also, right. So how do I calculate purity? Purity is nothing but concentration C0i into yield I divided by summation of C0j yield j for all the j's. That means if there are n protein, I will have n terms like that all added up together with each other, okay. So that is called the purity, and as I said, if my window of collection is very short, I am going to get more pure protein, but my yield will keep going down. If the window of collection is very large, the yield will be large, but the purity will be going down. So I need to strike a balance, that is how I need to work at actually. So what is happening? You have a protein or a metabolite travelling in a solute or travelling in a continuous phase. Now this particular solute will start interacting with the stationary phase material. So there are many steps that is happening. The solute is transferred from the bulk solution to the surface of the stationary packing. So the solute is there in the bulk solution, so it will come to the surface of the stationary packing, then it diffuses into the packing, it interacts reversibly with the packing. So this interaction, different types of interactions are possible, no. It is reversible interaction, it is not irreversible, because chromatography is always reversible process. We want to collect the protein and then we want to recover it, okay. So it is a reversible process. So there is an interaction between the surface and the protein, and of course later on there is going to be a desorption of this solute. It diffuses back to the packing surface, so it diffuses back to the top of the packing surface, and then from there it diffuses back to the bulk solution. So many steps are taking place here. So the solute from the bulk solution comes to the surface of the stationary phase, then there is a diffusion of the solute through the stationary phase, then there is a irreversible interaction with the stationary phase, then there is a desorption from the bulk right up to the surface of the packing, and then there is a diffusion from the packing surface into the bulk of the liquid. So each one could be controlling or slowing down the process. So depending upon which one is controlling, you will have different types of processes taking place actually. So ideally we would like to have more interaction between the stationary phase solute and the solute in the continuous phase. We do not want the other resistances to be playing a major role in this chromatography process. So there is something called the efficiency of the process or the number of theoretical plates. So the number of theoretical plates is given by n is equal to 16 Tr divided by Wb whole square, where Wb is the peak width at the base, that means the width of the peak at the base. Okay. So we are assuming a Gaussian distribution here, do not forget that we are assuming a Gaussian distribution here. Okay. So there are different types of equations available for this depending upon whether we are measuring the base width or whether we are measuring the half width maximum and so on actually, that means width at the half maximum and so on. So all these assumptions are based on a Gaussian distribution, but what happens if it is not Gaussian? Okay. There is another relationship that is called the Dorsey-Foley equation for calculating the number of theoretical plates, okay, that is given by this relationship, and the assumption here is the peak is not uniform with respect to the center. So there is a non-uniform region between the left side of the center and on the right side of the center. So if this width is A, that is on the starting side, and B, that is on the ending side, then the number of theoretical plates is given by 41.7 Tr by W.1 divided by A plus B, A by B plus 1.25, where A plus W 0.1 is nothing but A plus B, that is this width, okay, and Tr is your retention time. So this particular relationship takes care of the differences in the symmetry of the chromatogram or the spectrum that is leaving the column. So we talked about plate height and we talked about number of plates, and we said smaller the plate height better it is, that means it is more efficient. So how do you reduce this plate height? We can reduce it by reducing particle diameter in the matrix. So I can make the particles very fine, but there is a disadvantage. If I make particles very fine, you are going to have the liquid flowing through encountering a lot of resistance. So the pressure drop increases, that means I need to increase the pump pressure. Reducing column diameter, when I reduce column diameter for same throughput, again I am going to increase the velocity of the liquid flow through the column. So again I am going to encounter pressures and forces. Changing column temperature, yes I could change column temperature, but then again if I am handling proteins I do not want to affect the stability of the protein by increasing column. Reducing the thickness of the liquid film. So, if you have any liquid present on the stationary phase, if I reduce the thickness of the liquid film, I will be able to improve the plate height. Optimize the flow rate of the mobile phase. So, I need to adjust with the flow rate of the mobile phase, so the plate height becomes good. So, if your thickness of the liquid film especially comes into picture when we are talking about liquid chromatography, and the thickness depends on physical properties of the continuous phase such as viscosity, density, surface tension, dielectric constant, etc., and also how it interacts with the matrix, that is the stationary phase matrix. There is another term which is called the resolution. So, if I have two components present, how good the separation of these two components is, that is what resolution tells about. Is the separation very good, that means resolution is very good. If the separation is very bad, that means resolution is very poor. So, resolution is a measure of the separation of two components present in my mixture. So, it depends upon the retention time, it also depends upon the width at the base of the peak. So, resolution is given by 2 times difference in the retention time divided by sum of the width of the bases of the two components, or we can take based on the width at half maximum W, that is W half, then resolution is given by 0.589 delta T I j, that means the difference in the retention time of component I and j divided by average of the width at half maximum. So, if the width at half maximum for component A is something, width at half maximum for component B is something else, you take an average between these two and substitute here, and that is what is resolution. So, the resolution depends on many factors, it depends on column selectivity or separation factor, retention factor, capacity factor, number of theoretical plates, and so on. So, all these affect the resolution. So, we can get an equation for resolution in terms of all these separation factors, capacity factors, theoretical plates, and so on actually. So, resolution tells you how good the column is in separating two components. For example, I have two components and the output looks like this, they are well separated, the distance between these two is 6 sigma, then the resolution is 1.5. Okay. If the distance between these two maxima are 4 sigma, then the resolution will be 1. If the distance between these two are 3 sigma, then the resolution is 0.75. If the distance between these two are 2 sigma, then the resolution is 0.5. So, depending upon the distance, whether it is 2 sigma or 3 sigma or 4 sigma or 6 sigma, I get different numbers ranging from 0.5, 0.75, 1, 1.5 and so on actually. So, resolution tells you how good the peak maxima are or how far apart these peak maxima are. So, resolution between peaks improves with the L, that means if I have longer column I can move the two peaks slightly further apart, but it also leads to an increase in the elution time, that means the component will come out much slowly. So, the selectivity can be modified by changing the composition of the mobile phase, that means I can change the composition of the mobile phase, I can make it more polar or I can make it more non-polar, I can play around with the composition. Changing the column temperature, as I originally said, sometimes the proteins may be very sensitive to column temperature. So, we might not be able to play too much with column temperature, but if we are handling only small molecules or metabolites or drugs, then changing column temperature is an option. Changing the stationary phase, I can use some other stationary phase, sometimes using some chemicals, additives All these can also help in changing the selectivity of the chromatography process. There is something called peak asymmetry. Although we have been thinking that the peak leaving the column will look like a normally distributed Gaussian extremely symmetric, but it will not be so. It may have a front or a fronting, or it may have a tailing. That means the concentration may be dropping very slowly, that is called a tailing, or the concentration may be rising very slowly, that is called the fronting. So all these are possible, and all these are because of maybe the polarity of the solvent or maybe because of the stationary phase material. Okay. So sometimes you may have a very poorly packed columns, or there could be some sample injection problems, or the capacity factors may be very different. So all these are possible actually. So how do you calculate this tailing factor? We know what is A, we know what is B. So A plus B divided by 2A, and if you calculate that, generally this number varies between 0.9 to 1.1. So if it is around 1.1, that means B is more, so you get a tailing. If it is less than 1, that is around 0.9, that means A is more, that means you will have the fronting. So if you calculate this A plus B divided by 2A, and if it comes out to be less than 1, we can say it is a fronting type of situation, and if it is greater than 1, you may call it as a tailing type of situation. So this is possible because of so many factors, as I said, because of the selection of solvents, because of the type of packing we are using. Sometimes we make mistake during injection of the solute mixture or the protein mixture. So all these could cause these problem, but ideally one would like to have a Gaussian type of distribution or a normal type of distribution. Okay.